So hello everyone, I hope that you're all doing well and welcome to this third webinar on energy balances. So today we will learn how do we move from energy statistics to energy balances and also how to calculate CO2 emissions. So this is the agenda for today. So for the next 2 hours, we'll look at at energy balances and CO2 emissions, and this will close this week's program, and then next week we will look at one last session on statistics on prices and energy efficiency indicators, and then you will start with the modeling sessions. So very quickly, now you're familiar with this slide on housekeeping rules. So everything is virtual. If you have any urgent clarification, please raise your hand. And if you have any questions, write it down in the Q&A box. At the end of each presentation, there's a question and answer session. And so we will be able to answer any question you might have. Or if you have any other additional questions, please write to me, to Darlene, or to the Africa Program email address. So as you know, the energy balance, it's a natural starting point to study the evolution of the domestic energy market, to forecast energy demand, to monitor impacts of energy policies, and also to assess potential areas for action. And today, our session will be divided into 5 parts. First, we will see what is an energy balance, how it differs from the commodity balance, and how the IEA energy balance is constructed. Then we will see the importance of calculating an energy balance and the advantages you can derive from it, such as generating indicators for analysis or for CO2 emissions estimates. We will also study the principles of creating an energy balance. We will look at the IEA methodology and definitions used with a focus on calorific values. I will also show you how an energy balance looks like and how the transformation of energy happens in the balance. Finally, we will see how, with the data from the energy balances, we can calculate the CO2 emissions from fuel combustion. So let's get started. So the energy balance, it's a presentation of the basic supply and demand data for all fuels in a manner which shows the main fuels together, but separately distinguished and expressed in a common energy unit. The energy balance, it takes the form of a matrix where the columns represent the different energy sources, so the products categories, and the rows represent all the different flows grouped in 3 main blocks. So you have the energy supply, the transformation energy use, and the final consumption block. To develop an energy balance from the set of commodity balances, there are 2 main steps. First, all the data are converted to a common energy unit, also allowing to compute a total column. And second, some reformatting is performed in order to avoid double counting when summing all the products together. This format, it allows the easy comparison of the contributions each fuel makes to the economy and their interrelationship through the conversion of one fuel to another. So with an energy balance, you get the global picture of the energy situation of a country. So another way to present an energy balance, it's through the Sinkey Flow, which is a graphic format. It is exactly the reverse matrix with the products and flows, and it gives you a quick visual picture of the energy sector of the country over time. The arrows, it shows the energy flows from production to final consumption. And you can see that the flows can be combined, splitted, and traced through a series of events. The width of the arrows are proportional to the flow quantity. And so, for example, here you can see the Africa Sinkey Flow, and on your left side you can see from production. So for production of different fuels, so you have oil production, coal production, biofuels, and waste production. And then you can see how, for example, for biofuels and waste, some of it is used in other transformation to produce, for example, charcoal, and the rest is used in the other sector. So on your right, complete right, you can see the total final consumption sectors. So you have industry, transport, other non-energy use, and also, if you go on the IEA website, you have the link here on the screen. You can also use the timeline to see for your country how from, for example, from 1971 to today, how the Sankey evolves, which fuels increase, which one is decreasing, which sector is taking the most importance. So it's a very interesting and visual tool. For the moment, for Rwanda, the Sankey is not yet visible, but we are working on having this available in the coming month. So very soon you will be able to show this, to have this for Rwanda as well. So now let's do some interactive questions to test a bit your knowledge on energy balances. So please start connecting to the website www.mentee.com. I will do the same. Yeah, so please connect to www.mentee.com and use the code that appears up on the screen here. So 28, 77, 64, and 19. So I put it in the chat box as well. So I just put the code in the chat box: 28, 77, 64, and 19. Okay, let me. So the first question is it possible to have a statistical difference which is 0 in a statistics table in physical units and which is not 0 in the related energy balance? So please think about it. For example, you have your energy balance for coal in tons, and there you don't have a statistical difference. And then when you convert into an energy balance in, for example, in KTOE, is it possible that suddenly you end up with a statistical difference in energy unit when in physical units this did not exist? Think about it. So we have 4 persons that have replied, 3 that is saying yes, it's possible, and 1 that is saying no, it should always be the same. Give you some more time to think about it. And please, I really recommend all the participants to participate. It's a nice way to interact with you. So is it possible to have a statistical difference which is equal to 0 in the statistics table in physical units and which is not 0 in the related energy balance? So let's look at the right answer. The right answer is yes, and we will look at this in more details in the presentation. But if you're not using appropriate calorific values for the different flows in the energy balance, then you might end up with a statistical difference in energy units, even though if in the physical unit it did not exist. So again, I emphasize the importance of collecting appropriate and accurate calorific values. Next question. In an energy balance, you see a positive number in the total column of a transformation flow. Is it possible? So try to think of the energy balance table. You have your different columns for each flow. And then you have this total column, which is the sum of the flows. I'm sorry for the cough. And in the transformation block, you will see that, for example, you have crude oil that is used in a refinery. Let's think of the refinery process transformation. So you have crude oil that enters your refinery, and you have some oil products that is that's the output of the refinery. And then in the total column, you're summing this row. And as you know, in an energy balance, there's some sign convention. The Mentimeter link, sorry, I'll just put this. So you connect to www.mentee.com, and then you put the code that I put up in the chat. I'm just replying to this chat so that everyone connects to Mentee. I think sometimes I can also put this link here directly. If that's useful. Yeah, so I was saying for this question, for you to understand well. So in the total column, it's summing these the crude oil and the oil products. And can you then get a positive number there? Because there's a sign convention in the energy balance. So your input will be with a negative number and your output will be with a positive number. Only in the transformation process you have this sign convention in an energy balance. So think about it. For example, you're putting 100 kTOE of crude oil in a refinery. Is it possible for you to get then 110 kTOE of oil products? And then in your total column, you will do minus 100 plus 110, and then you get a 10 in your total. So think about efficiency. So here you have 3 possible answers in this Mentee question. In an energy balance, if you see a positive number in the total column of a transformation flow, is it possible? Yes, this means that the transformation efficiency is very high. No, transformation outputs are always equal to the inputs and total are always equal to 0. No, totals are always negative because transformation efficiencies are always lower than 100%. So 3 possible answers here. I'll give you some more time to reply to this. So we have more participants that saying no. Totals are always negative. So let's look at the right answer. So most of you got it right here. In the total column, it should be negative because transformation efficiencies should be lower than 100%. So in my example of crude oil and oil products, so if you're putting 1 kTOE of crude oil in a refinery, you cannot get 110 kTOE of oil products, especially in energy terms. You can't create way more energy, and you cannot have then like a 110% efficiency. But normally you can have like, you put 100, you get 95 kTOE of oil products. In physical units, it can be a bit tricky, a bit different, because in physical units, when you're putting in tons, for example, because of the density and all of the crude oil, you might end up with more in terms of oil products. But in energy terms, you cannot. So in energy, that's not possible. So when you're checking the energy balance and you're running a check on this total column, and you find something positive there, then this is something that you should query with the country. So for now, we'll pause here on mentee. We'll get back to mentee later, and we will start with the presentation now. Now, let us see in more details the importance of calculating an energy balance and what you can derive from it, such as generating indicators for analysis and CO2 estimations. The energy balance is a way of reporting energy data in a common unit and with products aggregated by category. It has many benefits and uses. By presenting all the data in a common energy unit, the energy balance allows users to see the total amount of energy used and the relative contribution of each different source for the whole economy and for each individual consumption. It also allows comparison of the shares of each source in the energy supply of a country and in each sector of economic activity. Different countries can be compared when they are calculated with the same methodology. With an energy balance, you can develop various aggregated indicators, such as consumption per capita or per unit of GDP, and to estimate CO2 emissions from fuel combustion. A country can determine its dependence on energy imports or exports. With an energy balance, it is possible to analyze energy efficiency. The statistician also uses the energy balance as a high-level check on the data accuracy, as large statistical differences in energy units, apparent energy gains, or large losses in transformation processes may all indicate underlying data problems. Also, it allows us to have a good basis for making forecasts and projections to achieve climate goals and to check that policies in place are well implemented. If you want to exploit the full potential of an energy balance, it is recommended to combine energy statistics with economic indicators. These new aggregated indicators allow us to understand how energy impacts society and economy. For example, we can calculate the energy intensity and self-sufficiency of a country. Energy intensity is a measure that is often used to assess the energy efficiency of a particular economy. The numerical value is traditionally calculated by taking the ratio of energy supply to gross domestic product, indicating how well the economy converts energy into monetary output. The figure on the left side shows us how primary energy use and GDP have changed globally over time relative to a normalized year of 1990. As you can see, GDP and total energy supply are decoupling, and this can be due to several reasons such as structural changes and efficiency improvement. In sub-Saharan Africa, the energy intensity is decoupling less quickly than globally.
Obviously, low energy intensity is the desired goal because it represents an efficient allocation of energy resources to generate wealth and a high quality of life. So it is logical to expect energy intensity to increase and for GDP and energy use to be closely coupled during the initial stages of development of a nation, since the early years of access to electricity and utilization of more abundant energy includes many energy-intensive activities. The developing economies will need to produce a tremendous amount of cement for roads and buildings, as well as steel for automobiles, appliances, and telecommunication infrastructures. These will be new users, some of which will naturally be energy intensive. We can also compare countries to see where each other stands for. In this graph on the right side, you can see that OECD countries are less energy intensive compared to non-OECD countries for the reasons I mentioned before. In sub-Saharan Africa, the differences between countries are quite large. Some countries, such as Democratic Republic of Congo, is more energy intensive compared to Ghana. Another indicator is self-sufficiency. The energy self-sufficiency rate is the ratio between national primary energy output and consumption of primary energy in a given year. This rate may be calculated for each energy types or overall for all types of energy. A rate of over 100% indicates a national production surplus in relation to domestic demand and therefore net exports. For Africa, if you remove biofuels from the energy mix, then the self-sufficiency declines a lot. In sub-Saharan Africa, a very high self-sufficiency rate is due to the top oil producers. Now, if we compare the self-sufficiency by country, we see that again there are differences because of biofuels and waste. For example, for Uganda, the self-sufficiency can seem very high at around 90%. But if we look at the energy balances, we see that there is a very high share of traditional biomass in the energy mix. And if not accounted, we see self-sufficiency drastically decreasing to 16%. Conversely, for Nigeria, who is a strong oil producer, self-sufficiency even increased because most of the oil is exported and biofuels consumed domestically. However, concerns for oil producers in Africa are on the midstream infrastructures, namely refinery, and countries will indeed import most of the finished products beside a large national oil production. In the case of Ethiopia, if we remove biofuels from the self-sufficiency, then Ethiopia is producing only 20% of its energy demand. Another indicator is the residential consumption per capita. So how much are we consuming at home? In this chart, we can see that the difference between OECD countries and sub-Saharan Africa is quite large. In sub-Saharan Africa, we consume 50% less energy in residential sector compared to OECD countries. However, traditional biofuels used in sub-Saharan Africa is quite large and inefficient, and the useful energy consumed per capita is much lower. This is how the picture looks like if we exclude solid biofuel consumption, which is very inefficient consumption per capita in sub-Saharan Africa. we see that the gap with the OECD is even higher and consumption per capita is very low. Now, let us look at the methodological assumption underlying energy balances. As you know, energy data are generally collected independently across different commodities. To develop an energy balance from the set of commodity balances, there are two main steps. The first one is to convert the natural units in the different commodity balances, that is for coal, oil, gas, renewables, and electricity, to the chosen energy unit. Here it is kiloton of oil equivalent in the IEA balances, but many countries use terajoules. By multiplying by the appropriate conversion equivalent for each natural units, which are calorific values. The second step is some format changes. We need to do some reformatting in order to avoid double counting when summing all products. We need to rearrange the converted commodity balances along one another, rearrange certain of the rows, and introduce a sign convention in the transformation sector. What is a calorific value? It is the amount of heat obtained from one unit of the fuel, and it is the only way to convert a fuel quantity from natural units, that is mass or volume, into energy units, that is kTOE. It is very important to collect good quality calorific values in addition to good data in physical units. As you can see, in this commodity balance, there is no statistical difference. But when we convert to the energy balances using calorific values, then a statistical difference appears. Why? If we look carefully at the calorific values in the middle table, you will notice that the calorific value for the input to electricity and consumption is different from the production and imports. This is something to query with the country. So as you can see, calorific values can be a good check for data quality control. Now, let us look into more details at the principles of an energy balance. The main methodological choices underlying energy balances that can differentiate the final balances layout across organizations are as follows. The IEA energy balance methodology is based on a common unit of account and on the calorific content of the energy commodities. The IEA balances are expressed in terms of net calorific value. The change from the original units to tons of oil equivalent implies choosing coefficients of equivalence between different forms and sources of energy. When constructing an energy balance, it is necessary to adopt conventions for primary energy from several sources, such as nuclear, geothermal, solar, hydro, wind, etc. For each of these sources, there is a need to define the form of primary energy to be considered. There are essentially two methods that can be used to calculate the primary energy equivalent of these sources: the physical energy content method or the partial substitution method. Also, temperature adjustments made by countries should also be taken into account. And finally, we have to know if the balance is based on a fiscal or a calendar year basis. First, we have to choose an energy unit. Then we have to choose the energy unit. It can be any energy unit. It can be British thermal units, ton of oil equivalents, joules, watt hours. The unit of account adopted by the IEA is the ton of oil equivalent, which is defined as 41.868 gigajoules. This quantity of energy is within a few percent equal to the net heat content of 1 ton of crude oil. The conversion of the IEA energy balance to any other energy units would be straightforward. The choice of the ton of oil equivalent is based on the history of the IEA creation after the first oil crisis. The difference between the net and the gross calorific value for each fuel is the latent heat of vaporization of the water produced during combustion of the fuel. This heat is lost and cannot be recovered. For coal and oil, the NCV is about 5% less than the gross. For most forms of natural gas and manufactured gases, the difference is approximately 10%, while for electricity and heat, there is no difference as they are not combusted. The use of net calorific values is consistent with the practice of the statistical offices of the European communities and the United Nations, and most importantly, it represents the useful energy. Generally, the IEA adopts country-specific, time-varying, and for some products, flow-dependent net calorific values supplied by national administrations for most products. For coal, the IEA has adopted specific factors supplied by the national administrations for the main categories of each quality of coal and for each flow or use. For natural gas and crude oil, specific factors have been used for production, imports, exports, and electricity generation based on consultations with experts from the national administrations. In the case of oil products, the IEA applies regional calorific values. So now we know how to convert combustible fuels in energy units, but what about nuclear, hydro, and other renewables? Why is it so important to compute this input, the primary energy equivalent? Because it is important to quantify the primary energy supply in order to calculate the total energy supply. A very important methodological choice is the definition of the primary energy equivalent for the electricity and heat produced from non-combustible sources such as nuclear, geothermal, solar, hydro, and wind. The information collected is generally the amount of heat and electricity produced, represented in the balance as an output of the transformation. Conventions are needed to compute the most appropriate corresponding primary energy input to the transformation, both in forms and in amount. For each of the following sources, that is nuclear, geothermal, solar, hydro, wind, tidal wave ocean, and solar PV, there is a need to define the form of primary energy to be considered. For instance, in the case of hydro energy, a choice must be made between the kinetic energy of falling water in the turbines and the electricity produced. For nuclear energy, the choice is between the energy content of the nuclear fuel, the heat generated in the reactors, and the electricity produced in the nuclear reactor. For solar photovoltaic electricity, the choice is between the solar radiation received and the electricity produced. The principle adopted by the IEA is that the primary energy equivalent form should be the first energy form downstream in the production process for which multiple energy uses are practical. The application of this principle leads to the choice of the following primary energy forms: heat for nuclear, geothermal, and solar thermal, and electricity for hydro, wind, tidal wave ocean, and solar photovoltaic. We have now identified the form of the energy input, but now we need to quantify it. There are essentially two methods that can be used to calculate the primary energy equivalent of these energy sources. The partial substitution method, which at the IEA we do not use anymore, and the physical energy content method. The physical energy content method uses the physical energy content of the primary energy source as the primary energy equivalent. As a consequence, there is an obvious link between the principles adopted in defining the primary energy forms of energy sources and the primary energy equivalent of these sources. For instance, in the case of nuclear electricity production, as heat is the primary energy form selected by the IEA, the primary energy equivalent is the quantity of heat generated in the reactors. In the absence of country-specific information, the IEA estimates the primary energy equivalent from the electricity generated by assuming an efficiency of 33%. This is derived as the average efficiency of nuclear power plants across Europe. For geothermal electricity, the primary energy equivalent is the quantity of heat, and a similar back calculation is used when the quantities of steam supplied to the plant are not measured. So assuming a thermal efficiency of 10%. This figure is only approximate and reflects the fact that the steam from geothermal sources is generally of low quality. If data for the steam input to geothermal power plants are available, then they are used directly as primary energy equivalent. Similarly, for solar thermal plants, the heat supply is back calculated assuming a 33% efficiency of conversion of heat into electricity, reflecting relatively low working temperatures, although central receiver systems can reach higher temperatures and therefore higher efficiencies. In the case of hydro, wind, and solar PV, as electricity is the primary energy form selected, the primary energy equivalent is the physical energy content of the electricity generated in the plant, which amounts to assuming an efficiency of 100%. So when the primary energy form is heat, we have losses. Let us see a few examples to illustrate this concept. For wind, as we have an implied efficiency of 100%, so with 1000 TOE of electricity produced, the primary energy equivalent is 1000 TOE of wind. In the case of nuclear, as the implied efficiency is 33%, so for 1000 TOE of electricity produced from nuclear, the primary energy equivalent is around 3000 TOE of nuclear. In the case of geothermal electricity, as the efficiency is 10%, so for 1000 TOE of electricity produced from geothermal, we need 10,000 TOE of geothermal. For geothermal heat, the efficiency is 50%. So for 1000 TOE of heat produced, we need 2000 TOE of geothermal. Now, let us look again at the energy balance in tabular format and how to read it. These are the key elements to understand in an energy balance. We have three distinct blocks. The top part, which is the energy supply block, the middle part, which is the transformation and energy use part, and the last block, which is the final consumption. The last two blocks are what we refer to as demand. Only production of primary products are shown in the production row in order to avoid double counting. Secondary products are shown in the transformation block. That is why for oil products and electricity, the production cell is 0. The total energy supply row allows users to see the total amount of energy used and the relative contribution of each different source. Do you think this country is producing oil products? In the transformation block, there is a sign convention. Negative values represent an input and positive values represent an output. Transformation losses appear in the total column as negative values. In the total final consumption block, you have all the different sectors consuming fuels such as industry, transport, residential, and non-energy use. In this table shown in this slide, the energy balance is cut. That is why in the total final consumption, you are seeing only industry, but the table continues. As all fuels are reported in the same unit, then we are able to compute the total products column. In the transformation sector, the negative value in the total cell represents losses of the transformation process. I hope that this presentation has helped you understand some of the dynamism of the energy balances. Here are some key takeaways from the balances. Good energy balances are a compact source of energy information and is very convenient to use. However, a good energy balance requires good quality statistics, and not only in terms of data, but also calorific values. It also enables statisticians to run accurate checks of energy statistics, such as efficiencies, losses, etc. Also, they are the foundation for basic energy indicators, energy account, CO2 emissions estimates, and for modeling.
So now we'll just pause here to take some questions. So please send us any question you might have on energy balances. I've been joined by Taylor. So if you have any questions regarding the methodology, the construction of the energy balance, I see a raised hand from Martin. Hello, Martin.
Hello, Zakia.
Hi.
Thank you for the session. I'm very, very much interested in this session because I think some of the challenges we've had, actually, normally, I think annually we provide voluntary reports for SDG indicators, and have been having challenges of having data on SDG 7.3.1 on energy intensity due to lack of data on energy balances. I don't know, maybe it was just a few hours of training, but probably we shall have some other bilateral sessions maybe to make sure that we have the capacity to produce these annual reports by ourselves.
Yeah, definitely. I mean, we can have a follow-up discussion on this. There will be a session on the SDG 7 not next week, I think in a few weeks' time for Rwanda. But yeah, I mean, happy to discuss bilaterally with you. We can also invite other colleagues that that work on these indicators on our side. I don't know if you are aware, but the IEA has just updated, I think, I don't know if it was just updated now. We have a dedicated page on SDG 7.1 indicators. SDG, not only 7.1, but the others as well, all the SDG 7 indicators. And I think we are publishing for Rwanda as well, if I'm not wrong, for those indicators. Let me just check right now on the IEA website if I can get hold of this page, and then I can put it in the chat box. If other colleagues have any other questions, please don't hesitate. I think it's this page, yes. It's not yet updated for 7. Let me, if I type Rwanda here. Yeah. Yeah, it will be this page. I think they are working right now in updating it. So I'll put it in the chat box. I know my colleagues are working on this update, and I think that's why it's offline now, because they are replacing it. But on this page, you should be able to have data for Rwanda as well, for the SDG 7 data, and also projections.
That would be good.
Yeah. I think there's a question in the Q&A box. From Sumya, if we are using the same fuel for, say, HCGO, but from different batches with varying calorific values going in the same tank, is there a formula we can use to calculate our energy balance? Would you like to reply to this one, Taylor? What is?
Sure. So in this case, you would want to get a weighted average for the CVs. And this would be similar to the exercise yesterday in terms of finding the weighted CV average. So that would be additional work, of course, in terms of figuring out how much of each fuel you are using and how the different weights of fuels flow. But overall, as you've seen, the energy balance is very high level, so we wouldn't have that level of detail in the final balance. So you would need a weighted average.
Yeah, it would be good to know from the different batches, the quantities and the calorific value for each batch, and then you can make a weighted average.
And in the balance, your final balance will show, hopefully, if you've done this correctly, because if there's the average isn't weighted with the NCVs, then you'll find in energy terms, there'll be some statistical differences. So that can also help you in terms of figuring out if the NCVs have been calculated correctly.
Yeah. I hope, Sumya, that this is clear. Any other question? There are, I mean, if you want to learn more on energy balances, it's good also if you can take a look at the IEA Energy Statistics Manual, and also the UN IRES manual, which are good guidelines to support countries in developing energy balances, to understand well how it works and how to use the data from the energy balance and interpret them, because sometimes we have numbers and some analysts, models, policymakers, they don't interpret well the numbers. So it's always good to know well how these numbers have been constructed, the methodology used, why is it different from another number, from different organizations, from another ministry. So it's good to understand what's behind numbers. Please don't hesitate to ask us or to make any comments, sharing your experience with energy balances. No question? Okay, I think then we can move on with the second part. Thanks a lot, Taylor, for joining.
Thank you.
We'll do just another mentee, and then we'll move on to CO2 emissions. So it's still the same mentee code as before. So if you still have it open, or if you have not, then please connect to www.mentee.com and use the code 28, 77, 64, and 19. So it's the same code as before. And answer this question. So if you have your energy balance calculated with a reasonable level of granularity, can you estimate your country's CO2 emissions from fuel combustion? You have three possible answers. Yes, you take the total energy consumption and you multiply it by a fixed conversion factor provided by the IPCC. No, you need more information. Or yes, you can use the standard IPCC carbon intensity for each fossil fuel burn in the country. So please connect to the mentee website and answer this question using the same code as earlier. So let's look at the right answer. And all of you got it right. So if you have your energy balance with a reasonable level of granularity, then you can use the standard IPCC carbon intensity for each fossil fuel, so for coal, oil, and natural gas, and multiply it by the different flows of your energy balance. And so another question, which is the most CO2 emitting fuel per unit of energy? So from charcoal, LPG, fossil coal, natural gas, you have to rank it, which one emits the most to the one emitting the less. So here, think about the different fuels. So liquefied petroleum gas, it's an oil product. So rank it from the most emitting to the least emitting fuel. I just gave you a hint. Excellent. So very good. Usually coal is the most emitting, and natural gas it's the least emitting. For charcoal, here we need to be. It depends how you categorize charcoal. For example, at the IEA, for us, charcoal it's a renewable. It's a even though it's how do I describe it? It's under bioenergy and waste, so it's not really under fossil fuel combustion. So we need to be careful with the methodology, but excellent. We have a comment from Jovin in the Q&A box who says, in Rwanda, we have limited energy resources on the supply side and complex of demand structures, so for energy consumers and users, and energy transformation is also somehow complex. Mainly Rwanda energy, more specifically cooking fuels, rely on biomass, and main consumer it's the household for both biomass and electricity, while household data and services sector data collection remain very challenging. Reasons why mostly we rely on assumptions. Yes. So what could you suggest for further development of Rwanda energy statistics so that later or soon we will have an official published energy balance? Remember that we cannot ensure demand forecast and supply without baseline, which is the energy balance. So yes, I know, I completely understand the challenges that you're facing. So I think to further develop Rwanda statistics, we need to have like a solid energy statistics system, and to really strengthen it through different means. First, the framework, having a proper statistical act to when you for data collection, to make industries report data, and also to have the proper resources, whether financial, in terms of staff. It's very important to also secure this. And also training of the staff, our training is a very good start on this, making sure that staffs have the proper training and resources, and also to invest on technology, like using innovative tools to make surveys, whether to process data, also to disseminate the data. It's very important. And using the proper, regarding the data itself, having a solid collection process, also how the way you process the data, you check the data, having proper checking tools. A good quality data is very important, and dissemination, what are the different dissemination tools, or whether you publish on websites and all. And regarding surveys, developing surveys, we know it's costly, but also I think cooperation among different ministries, it's very important. If you can try to use existing surveys to add more questions rather than creating new surveys from scratch, I think that should be taken into account and used whenever possible. And also see what are the good practices from other nearby countries with similar characteristics as Rwanda. See what other countries that have already developed on this side, see what are the best practices from them, what are the tools, get advice from other countries. This is very useful. So it's good to communicate within industries, but also with other countries to see how we can make use of of existing maybe materials and surveys that you can use and copy and use. Right now at the IEA, I'm working on developing a roadmap to support countries to strengthen their national statistical system. We just started a few weeks ago this project, and hopefully in Q3, by the end of the year, we should have it finalized and shared with countries. We will soon get in touch with countries. We are trying to organize consultations with countries to discuss this roadmap. So Jovin, if you're interested, I would be very happy to get in touch separately and organize in the coming days very soon. I mean, I should have already sent this invitation, but because I'm sick this week, I haven't been working a lot. But I will contact soon Jovin and other colleagues in Rwanda in order to have a meeting to discuss this roadmap. I think it falls really into what the challenge you're facing in Rwanda, and how can we strengthen your national statistical system to tackle all these challenges you're facing in collecting residential data, household consumption for biomass and all. So yeah, so I think we will follow up on this bilaterally, and hopefully we can work together on this. So I hope I have answered some of your question, Jovin. Now let's move. Yeah. So let's move to the presentation now.
This chart represents the global CO2 emissions from fuel combustion. The share of the OECD countries in global emissions has decreased from over 55% to around 35% in less than 20 years. However, the global emissions have increased at a pace of around 2% per year, mostly driven by the emission growth in the non-OECD countries. The small blue line on top represents the sub-Saharan Africa emissions, excluding South Africa, and the orange line represents the other African countries. Despite a strong increase in the past 20 years, they correspond to only 4% of the global CO2 emissions, while representing about 15% of the global population. Credible and validated energy data are pivotal in providing high-quality emission estimations and greater confidence in the policy analysis. Access to comprehensive data enables detailed analysis of key sectors, fuels, and driving factors of emissions, both on a country-specific and global levels. This figure represents the sectoral share of CO2 emissions in the OECD, non-OECD, Africa, as well as a few African countries. The electricity and heat generation correspond to about 2/3 of global energy-related CO2 emissions from fuel combustion. Disaggregated data allows allocating the emissions associated with power generation to the end sectors and provide a more complete understanding of real drivers of CO2 emissions. The graph on the right represents the sectoral emissions after reallocation of power generation emissions to the end sectors. As you can see, in the OECD countries, buildings, transport, and industry are together responsible for about 85% of total emissions, while among the non-OECD, industry alone represents more than 50% of the total share. In the sub-Saharan Africa, however, transport remains the highest source of emissions, representing 50% of the total. Detailed emissions data enables populating matrix, which can be used to discuss the macroeconomic driving forces behind CO2 emissions and provide insightful input for effective energy and climate policy making. The formula on the top is known as the Kaya identity, which allows decomposition of the total CO2 emissions into 4 macroeconomic factors: population, GDP per capita, total energy supply per GDP, and CO2 emissions per unit of total energy supply. As illustrated in the graph on left, among the OECD, decreasing the energy intensity of the economy alongside lower carbon intensity of the energy mix have been driving the emissions down. On the other hand, among the non-OECD countries, increase in population, GDP per capita, and carbon intensity of the energy mix have been driving upwards trends in CO2 emissions, while the reduced energy intensity is slightly offsetting this increase. In Africa, the increase in population and wealth are the main drivers of emissions increase. Most of you are perhaps already familiar with the concept of greenhouse effect. CO2 alongside methane, N2O, water vapor, fluorinated gases, and ozone are known as greenhouse gases. The greenhouse effect refers to the circumstances where the short wavelengths of radiation from the sun pass through these gas molecules, but the longer wavelengths of the re-radiation from the Earth's surface are unable to pass through them. The trapping of the long wavelength radiation leads to more heating and a higher resulting global mean surface temperature. CO2 is the major contributor to global warming, and combustion of fossil fuels is the main source of global anthropogenic CO2 emissions. The burning of fossil fuels affects the concentration of CO2 in the atmosphere. Before the Industrial Revolution, the amount of CO2 in the atmosphere was about 288 ppm. We have now reached about 414 ppm, and we are on the way to doubling the amount of CO2 in the atmosphere by the end of this century. There's currently a strong scientific consensus globally regarding the role of emissions caused by the anthropogenic activities in increasing of global mean temperature. According to the IPCC special report of 1.5 degrees C, global temperature increases by the end of the century is likely to reach up to 5 degrees C above the pre-industrial levels if the current policy trends are continued and no significant action is taken. The United Nations Framework Convention on Climate Change, UNFCCC, is an international treaty adopted in 1992 to address climate change. Starting 1995, the parties to the convention have met annually to assess progress in dealing with climate change. In year 1997, the Kyoto Protocol was adopted and established legally binding obligations for the developed countries to reduce their greenhouse gas emissions. At the 21st Conference of the Parties, or COP21, in Paris, countries approved a new global climate change agreement, the famous Paris Agreement. The aim is to limit the global average temperature increase to well below 2 degrees C, with efforts to limit this further to 1.5 degrees C. The Paris Agreement was adopted in 2015 and came into force in 2016, with 187 countries ratifying it. In COP26, which is planned to be held in November this year, countries are expected to communicate or update their national climate targets. The IPCC, with the help of IEA, has developed and refined an internationally agreed methodology for the calculation and reporting of national greenhouse gas emissions. The guidelines is called the 2006 IPCC Guidelines for National Greenhouse Gas Inventories Reporting, which is caused and used by the countries to report their emissions to UNFCCC. The IEA estimates of CO2 emissions are based on this credible international methodology. It's important to note that according to the IPCC guidelines, countries report their emissions under 5 different categories, as listed on the page. IEA deals with category 1, which corresponds to energy-related emissions only. Moreover, the energy-related emissions are divided in 3 subcategories under the guidelines. And the IEA estimates cover category 1A, which corresponds to the CO2 emissions resulting from fuel combustion of fuels only. However, as shown by the graph, energy is at the core of the greenhouse gas estimation, and the CO2 emissions from fuel combustion, which are covered by the IEA analysis, correspond to around 3/4 of total global greenhouse gas emissions. IEA CO2 estimates are based on globally recognized guidelines throughout the process. Our data collection process starts at the country level from national statistical or energy offices, where we collect energy data in physical units in the form of IEA energy statistics, which you are by now familiar with. From there, and based on the international recommendations for energy statistics as published by UNSD, and with the help of the net calorific values for various fuels, this information is put together in energy terms and forms the IEA energy balances, as it was discussed in detail earlier today by my colleague. Finally, and with the help of the default emission factors and methodology provided by the IPCC guidelines, IEA CO2 emissions are estimated. It's important to note that the IEA estimates of CO2 emissions from fuel combustion are a global database obtained following harmonized definitions and comparable methodologies across countries. However, they do not represent an official source for national greenhouse gas inventory submissions to UNFCCC. The IEA uses the simplest, the Tier 1 methodology to estimate CO2 emissions from fuel combustions based on the IPCC 2006 guidelines. Based on the Tier 1 method, the CO2 emissions from fuel combustion for a given fuel are calculated by multiplying the amount of fuel consumed in energy terms by the default fuel-specific emission factors provided in the IPCC guidelines. The computation follows the concept of conservation of carbon, which assumes that all carbon contained by the fuel burnt is oxidized and emits CO2. Emissions are then summed across all fuels and all sectors to obtain the national totals. It is also important to note that various fuels have different emission factors. For example, as you can see on the graph, combustion of a unit of a carbon-intense fuel, such as a blast furnace gas, corresponds to around 5 times of CO2 emissions, comparing to when the same amount of natural gas is combusted. And now to conclude, there's a scientific consensus regarding the role of anthropogenic CO2 emissions in increasing the greenhouse gas concentration in the atmosphere and the global warming. Effective emissions mitigation requires collaboration on a global level, and up-to-date and accurate information on greenhouse gas emissions are essential for effective climate policy making. And most importantly, the greenhouse gas emission estimates are only as good as the energy statistics which underlies them.
So I hope that this presentation on CO2 emissions, the methodologies and how to calculate it was useful to you. I've been joined by my colleague Puya, who's an expert on CO2 emissions. So if you have any questions, please send it to us through the Q&A box, or you can take the floor as well just by raising your hand, and I will give you the permission to talk.
Thank you, Zakio. Hello, everyone. I would be happy to help if there's any questions.
Maybe it would be interesting to know if in Rwanda you are already doing this calculation yourself. What is the methodology you're using? Is it the same as the IEA? Do you report any data to IPCC?
Yeah, it would be interesting to know if anyone has any experience or such information of what is being done in Rwanda at the moment, because, for example, I know that you have recently in 2020 updated your nationally determined contribution, NDC, which are voluntary commitments submitted to UNFCCC under the Paris Agreement. And I can see that Rwanda has a target of 38% reduction in greenhouse gas emissions comparing to the business as usual by 2030. So it's interesting to know if what's being done in the country in terms of being able to estimate and track these emissions in order to be able to achieve the targets.
Yeah. So in the chat box, we have Sumya who is asking whether the recording will be available. So yes, so Sumya, we record all the sessions and we try to put it the same day or the next day on YouTube. So I'll put the link to the YouTube playlist where you can already find the previous sessions videos, and where by tomorrow you will also have today's session. And you also have the presentations on the Google Drive, which I think everyone by now have access. It's this one. Put it again in the chat box. Yeah. Let me see if there's any hands raised. Do you have any question on the topic CO2 emissions? Please share your experience also with us. No question?
Rwanda also has a net zero target right now by 2050, so an economy-wide carbon neutrality target, which is very good to see. It's already in a policy document.
No question? Anyway, if after the session you have any question, you can always write to me or to Puya directly. The email address, it's emissions@iea.org. I'll put it in the chat box. And if you have any query on the calculation of CO2 emissions, on methodologies, please don't hesitate to reach out to us, and we will be very happy to answer any question you might have.
Yes, definitely get in touch regarding any emissions, climate-related questions, and we would be happy to discuss and help and share experiences.
Yeah. Well, thanks, Puya, for joining.
No worries. Have a good day, everyone. Bye-bye.
Thank you. Oh, we have a question, Puya.
Okay.
In the Q&A box from Sumya. So regarding countries' CO2 emissions calculation, what are the most significant sectors that should be taken into account?
Okay. That depends really on the country because we have different types of economies around the world. But globally, majority of the important sectors that result in emissions are the transport sector, the industry sector, and the residential sector, which corresponds to most of the building sector. In African countries, what's more common is that typically the transport sector corresponds to the majority of the emissions. I don't know specifically on Rwanda. I have to look at the data to give you your country-specific proportion, but that's just an overall view.
Yeah, thank you. Any other question before Puya leaves? No? Then I think we can move to the exercise session.
Bye, everyone.
Bye, Puya. I'll just share my screen again. Okay. So this exercise, it's the continuity of the exercise that we did yesterday on commodity statistics. So if you remember, yesterday we had natural gas in million cubic meters, the commodity statistics. We look at calorific values. Then we converted the natural gas in energy terms in terajoules. We look at how to fix some errors. And we also look at electricity output, how to calculate an efficiency of a power plant for natural gas. So that was yesterday. And today, now we are asked to move to complete the energy balance. So we are provided with this energy balance for country A, and you are asked to fill the highlighted cells. So here, the first question is, why coal electricity plants sell C11? So C11, it's this number, minus 8,255, and crude oil refinery E12 are negative. So why are these two numbers negative? So if you remember from the presentation, these two are inputs to transformation, and so in an energy balance, these transformation inputs are shown with a negative sign. And if you look at oil products refinery F12, so F12, this is positive. This is positive because it's an output of the transformation. So you have your crude oil, which is an input with a negative sign, oil products with a positive sign, and then in the total, it's the sum. So we'll look at the total later in another question. So the second question is, using the results from the exercise 1, complete the simplified balance here for 2019. So yeah, use terajoule as unit. So here, for the energy balance, we will use terajoules and net calorific value. Remember that energy balances, it's always in net terms because we are only interested in looking at the useful energy, right? So here we need to complete the energy for natural gas, but also for hydro, solar PV, and wind. So here, remember, we are using net calorific values instead of gross calorific values. So we will need to convert from gross to net. So here you multiply by 0.9 because we said, again in the presentation, we say that for natural gas, the difference between the gross and the net calorific value, it's 10% for natural gas. For oil, for coal, it's 5%. So here, what do we do? For natural gas production, we go back to the exercise 1. So here you already have it, right? But it's in gross term. So for 2009, production 4,674. So here you just multiply it by 0.9 and you get your production. You do the same for imports, exports, stock changes, electricity plants. So you fill out everything based on this table here and you multiply by 0.9. For solar, hydro, and wind, here, what do we know? Here for electricity generation, you also have this information here. Here it's in gigawatt hour. In this table, electricity generation is also reported in gigawatt hour. So here you just link it directly. So for example, for coal, you come here and you just link it to 688 here. You put the value for natural gas, for hydro, wind, solar PV, wind, and the total, it's just the sum. So this is easy. And so for these three, we will have to report also this part. So for electricity plants, so the amount of hydro from electricity plants, given it's a 100% efficiency based on the methodology, we just have to convert it to terajoule because it's here it's in gigawatt hour, here it's in terajoule. So here you take your amount in gigawatt, you multiply by the conversion factor provided here, 1 gigawatt hour, it's 3.6 terajoule. So you get your data in terajoule here. And because it's an input, hydro, it's the input, you put the negative sign. Same for solar PV and wind, because of all three of them, you are taking the assumption of 100% efficiency based on the IEA methodology. So here, it's just the total times converted to terajoule. And here, in production, you just put it equal to electricity plants, but you remove the negative sign. So it's the same. So that's fine for the exercise 2. Exercise 3, looking at the refinery transformation, do you see anything wrong? Why? So if you look at refinery here, you have minus 4,495 input of crude oil, you have 532 output of crude oil, and you have a gain of 37 terajoule. So here we see that output is bigger than input. So the efficiency, if you calculate the efficiency, it's over 100%. So you get 107%. And this is not correct because energy gains are not possible in energy terms. As I said before, in volume units, this could have been possible where output from refinery is higher than input because of the lower density of the oil products compared to crude oil. But here, in this case, in the energy balance, it means that either the oil products or the crude oil is wrongly reported. So is it most probably the input or the output? So we just replied, it's either one of the two. And this can be because of wrong calorific values, incomplete observations, maybe some products are double counted. Here, if we look closely at the energy balance, it's most probably from oil products. Why? Because if you look at the raw statistical difference, you have a big statistical difference for oil products. So most probably there's something wrong in the oil products balance. Question 4. Calculate the CO2 emissions for total supply and electricity generation for each fossil fuel and as a total. So here, what do we do for coal? For coal, how do we calculate the CO2 emissions? So you take your amount of coal supply, so 8,600, you multiply it by your carbon emission factor for coal, which is provided here. And then you, in this case, you divide by 1000 because here you are in terajoule net. Your emission factor is ton of CO2 per terajoule, but here you're looking for kiloton of CO2. So you divide by 1000 to get kiloton of CO2. You do the same for natural gas. You take your total supply of natural gas, you multiply by your natural gas carbon intensity, and you divide by 1000. Same for crude oil, same for oil products. And the total, it's the sum of the different fuels. For electricity generation emissions, you take your amount of electricity, of fuel input for electricity generation. So for coal, the amount of coal input for electricity generation. Here you remove the negative sign because it's not needed for the calculation of emissions. You multiply by your coal carbon emission factor and you divide by 1000. You do the same for natural gas. For crude oil, there's no crude oil used for electricity generation, so it's just 0. Same for oil products, and the total, it's the sum of everything. So we did this calculation. The second question is, calculate for each fossil fuel generated electricity the CO2 emission intensity in gram of CO2 per kilowatt hour of electricity generation. Calculate also the average electricity carbon emission. So to calculate the electricity CO2 emissions intensity, you need to divide the emissions related to electricity plants by the electricity output. So here, what do? We take the amount of emissions from electricity generation for coal, and you divide by your coal electricity generation. And you multiply by 1000 to get a gram of CO2 per kilowatt hour. So take your electricity generation emission, divide for coal, divide by the coal electricity generation, and you multiply by 1000 to get the correct unit. You do the same for natural gas, electricity generation emissions, divided by the output from of natural gas electricity generation times 1000. And for the total, so you take your total electricity generation emissions divided by your total electricity output times 1000. So that was the exercise on on energy balances and CO2 emissions. I hope that this small practical exercise has helped you understand some of the concepts related to energy balances and CO2 emissions. Again, I reiterate myself here, please try to work out these exercises by yourself. And if you have any issue understanding anything or don't understand some of the solutions, please write to me. I will be more than happy to answer you, to guide you, and clear any doubts you might have. It's very important that I think you practice by yourself those exercises in order to understand well all the concepts that you have learned today from us. If you don't have any questions, then I think we have reached the end of our session today. I hope that the free statistical sessions we had this week was useful to you and you have learned something from us. And next week, next Tuesday, we will meet again to look at prices, energy prices, and energy efficiency indicators. There will also be an exercise in that session. So if you have time over the weekend to practice a bit, that will be great. And yeah, I think on my side, that's it for today. I wish you all a nice afternoon and nice weekend as well, because I will meet next Tuesday. Thank you, everyone. Bye.